We'll do this next problem again using the principle of inclusion-exclusion, and in this case we're going to count how many primes there are less than 100. This is something you could do by hand, but it's more the process, the way we're going to go about it that matters. So to begin with, I'm going to note the set of 4 smallest primes less than 10. So we're going to start off by thinking about 2, 3, 5, and 7, and there's a reason for that, and that is if we have a composite number, a non-prime, and it has the smallest prime p, and other primes like so. If the smallest prime, if p is greater than or equal to the next prime here would be 11, then p, q, ... will be greater than or equal to 11 squared, because p is the smallest prime. Q would have to be at least 11, which is 121, and that's greater than 100. So I guess what that is telling us is that if we have a non-prime number less than 100, a composite number as we call it, its smallest prime must be less than 100. So a composite less than 100 is divisible by 1 of 2, 3, 5, and 7, right? So we have our starting 4 primes. There's 4 of them. And what we're going to do is get rid of all the others, get rid of the composites, those things divisible by 2, 3, 5, and 7. So let's get rid of all the numbers less than 100 divisible by 2, 3, 5, and 7. So what we're going to do is say something like the following. The number divisible by 2 would be 100 divided by 2, and we'll take the floor function, and that's 50. That's easy. And then by 3, we'll take the floor function of 100 divided by 3 and get 33. By 5, we'll take the floor function of that, and that's just 20. That's exactly 20. By 7, the floor function of 100 divided by 7 is, sorry, get rid of a couple of those little marks there, is 14. 7 times 14 is 98. And so those are the individual counts, but unfortunately there's double counting and so forth, and so that's why we're using inclusion-exclusion. But these ones right here we'll add all of those in here, and then we'll take those that are divisible by 2 at a time, which are double counted here, and so we'll take 2 and 3. Let me go back to the green here. 2 and 3, we'll take 100 divided by 6, 2 times 3 in other words, and we'll get 16. And then 2 and 5, that'll be 100 divided by 10, and there's 10 of those numbers. So there's 10 of them divided by both 2 and 5, and of course those are counted both here and here. So there's 10 double counted here. And then we'll take 2 and 7, and that's 14. When we multiply 2 and 7, so 100 divided by 14, take the floor function, that's 7. And then the next one would be 3 and 5, because we've got all the ones with 2 in there. So 3 and 5 would be 15 there. 100 divided by 15, take the floor function, we'll get 6. And then 3 and 7, floor function divided by 21 will give us 4. And so that's 3 and 5, 3 and 7. We already have 2 and 3. So now we'll take 5 and 7. 5 and 7, and that'll give us 100 divided by 35. There are only 2 there, because 3 times 35 is 105. So those all are double counts that we will subtract. So those are 2 sets intersected, taking the intersections 2 at a time in inclusion, exclusion. And so now we'll do them 3 at a time and add those back in, because we've taken those out 3 times. So the 3 at a times would be 2, 3, 5. By all 3 of those would be numbers divisible by 30. All 3 of those would be 3 numbers. Okay, those 3 numbers were added in here. Let me get a blue here. They were added in here, like so, 2, 3, and 5. But they were subtracted out here, 2, 3, 2, 5, and 3, 5. Added 3 times, subtracted 3 times. So we're going to have to add them back in once, right? That's inclusion, exclusion. 2, 3, 7 gives us 42 down there. It's too much there. 100 divided by 42. Take the floor function, we'll just get 2. So here we've left out 7, here we've left out 5. Now let's leave out 3, so 2, 5, and 7. And that'll be 100 divided by 70. 2 times 5 times 7 is 70. There's only one of those. And then finally leave the 2 out, leaving the other 3 numbers, 3, 5, and 7. And that's 105. So I recognize that number. The floor function is 0, because that number is less than 1. So those we will add back in, and then we have one more to take, and that's all 4 of them at once, intersecting all 4. We'll take by 2, 3, 5, and 7, divisible by all of them. The product there is 210, so we just get a 0 there. This is a number we would subtract. Of course, it's only 0, so there's not much to do there. So the number would be, so the number divisible by 1 of 2, 3, 5, 7, or more would be 50 plus 33 plus 20 plus 14 minus 16 plus 10 plus 7 plus 6 plus 4 plus 2 plus 3 plus 2 plus 1, and that turns out to be, let's see, what do we get right here? Let me go ahead and get a black here and do that. This is 83, 103, 117 minus 26, 33, 39, 45, 45 minus 45, and then plus 6. I didn't include this these 2 zeros here, but that, you know, that would be a plus 0 and a minus 0. Right, so that's 117 minus 45 plus 6 is 78. So we have 100 minus 78 divided by 1 or more of 2, 3, 5, 7. So that leaves 22 numbers. Now what are those 22 numbers? Well, they're the numbers not divisible by 2, 3, 5, and 7, but by our analysis up above here, up in here, if a number is composite, product of 2 or more primes, it has to be divisible by one of those. So this includes all the primes other than 2, 3, 5, and 7, but it also includes 1, because 1 is not divisible by any of 2, 3, 5, and 7. So what we'll have to do is take 22 minus 1 is 21 primes. That 1 right there is because the 22 counts 1 primes other than 2, 3, 5, and 7. So that means it's 21 plus 4 for the 2, 3, 5, and 7, because they're excluded. They're divisible by one or more of 2, 3, 5, and 7. So they're 25 primes. Less than 100. So that's one where we've done an inclusion-exclusion with 4 sets.